Well, hello everyone. Good morning. Um, Looks like we don't have a ton of folks necessarily online just yet. If you're here, give a shout out in the chat or something like that. Let me know that you're here. And I'm, of course, looking for questions, but I figured I would sort of start out with a little bit of a discussion on the topics that we dealt with this week. And I was going back and looking at the lecture notes that I put out this week, and I did notice that there were a couple of little things that I didn't clean up in some of the lecture notes. Like at the tail end, I'd used some old lecture notes, and I'd left some old slides in there. So there were some slides that were a little bit superfluous to each particular lecture that was offered there. That were they were just left there, a little bit of riffraff there at the end. So hopefully that wasn't too confusing. The main lecture notes actually ended at each example problem like they sort of normally do. So hopefully that wasn't too confusing. I know it looked like there was a little bit of a prelude to some of the stuff that were coming up next. So the topics that we dealt with this week were expanding out of talking about not talking about just the particle in the box problem with this, which was sort of the beginning, the first elementary look at how the Schrodinger equation is looked at and solved. But we're actually talking now about some more solutions to the Schrodinger equation in one dimension, and specifically we talked about the solution of the harmonic oscillator in quantum mechanics, and then the solution to some scattering problems in quantum mechanics, and that was the topic of Wednesday's lecture from yesterday, and the lecture notes that maybe you haven't had a chance to look at yet, but they're for Friday, but they're all available for you to actually see. So hopefully that you've had a chance to look at those and maybe have some questions. So let's talk a little bit about the solution of the Schrodinger equation for the harmonic oscillator. And this one's a little bit complicated, but basically the idea is that the potential that you're looking at, the V, in this case is, oops, that's not a brush, there we go. The V that we're looking at, the potential that we are seeing for this is the, let me get a decent size here so you can see it better. The potential energy function is 1/2 kx squared, which, if you recall, another way to write that is in terms of omega. Omega, remember, is, I'm going to put omega squared, is k over m for the harmonic oscillator. This is the standard frequency, the natural frequency of oscillation that you get for the harmonic oscillator. Is related to the mass of the particle and the spring constant. So that allows us to rewrite this expression a little bit differently, so that the potential energy that's associated with it would be 1/2 times m omega squared times x squared. So that's just replacing k. That's no problem there. So then the harmonic oscillator equation then becomes, we got negative h bar squared over 2m. So this is not just this is the harmonic oscillator potential being put into the Schrodinger equation. Well, here's our wave function psi. Okay, so there's the standard part, the second derivative, and then you add the potential times the wave function, so that's adding 1/2 m omega squared x squared times psi, and that's supposed to be equal to some energy, the energy that's associated with the particle times psi as well. Okay, so that's the general harmonic oscillator version of the Schrodinger equation, and the question then is to how do we solve this? And it's not necessarily a simple solution, but the thing is, it does have there is some history for this equation in mathematics. In math, when folks first started looking at what they call the eigenvalue problem, which we talked about at the end of last week, at the end of the last discussion we had last week, they were looking at the eigenvalue problem, and they were looking at situations where, you've got derivatives of some function, you know, derivatives of f or derivatives of y, whatever. You're looking for the derivative of a function. And then there were all these possible eigenvalue problems where, oh, you know, and where the extra term multiplying psi had some, you know, had some dependence on x. So this one is the one where it's, you know, I've got the second derivative of the wave function, and then there's some dependent, then there's some, you know, part of the equation is multiplying times x squared times the wave function, that equal to a constant times the wave function. So this is actually a sort of a general formula, and the people that looked at that, there was a number of folks that looked at it, but one of them that developed one of the folks that mathematicians that developed the solution for this particular class of differential equations was Hermite, Hermite, E. So the solution then, it turns out, is a set of polynomials times an exponential, like a you know, like the Gaussian, the e to the negative x squared sort of thing. So this actually has the form of what we call the Hermite equation. It turns out that it is an eigenvalue problem where there will be, you know, there's going to be a wave function psi of n, and then there's a set of wave functions that work, and that works for only particular energies. So this, again, it solves, again, an eigenvalue problem like we dealt with last week. The thing is, these solutions are kind of complicated looking. Like I said, it's some polynomial of order n, so it's like the 0th order polynomial is one in which it's x to the 0th power, so it's just a constant. It's not really a polynomial at that point. But then psi sub n is where n is equal to 1, and this is a polynomial like of first order in x, so it, you know, some constant times x. The nth order polynomial is, you know, their second, you know, psi sub 2 would be one that involves a polynomial of second order, so it's, you know, some constant times x squared, and it turns out that it's only the even power, so it's x squared plus a constant time, and all of these polynomials get multiplied times the Gaussian function, e to the minus x squared, with some constants in there as well. And then the energies that arise from it are specific energies. This problem is only solved for particular energies when particular wave functions get put in. It's not just any old functions, very specific functions, and the constant e only works out if the energy is a specific value of energy. And what we found is, well, what I did in the lecture notes is just say, well, let's look at the 0th order polynomial here, which is, I don't remember what it is off the top of my head. Let me have a look at my lecture notes. Let's see. The 0th order polynomial is, the 0th order polynomial was some constant. So I'll just call it A0. It's the constant goes along with the 0th polynomial, and then it was just e to the minus m omega x squared. So there's your, and then there's an h bar, just h bar, let me see, 2h bar. It's in there, so there's a 2h bar, and that's it. So that's, you know, for n is equal to 1. Or sorry, that's n equal to 0. And what I did is then I plugged that equation, that this solution, this psi, into this equation here, and I figured out what e had to be. I just solved for e. So when you plug this, you take the second derivative. So this is a little complicated, but what you find is that this implies that e, the energy associated with that particular solution and no other, is equal to 1/2 times h bar omega. And what you would do next is you'd say, well, what's psi 1? Well, you'd look it up, and psi 1 is a little more complicated. But just to give you a sense of what it is, psi 1, just to remind you from lecture notes, is some other constant. It's a1, so this is kind of your normalization constant. And then you got the square root of m times omega over h bar. Okay, the square root goes, h bar goes in the square root as well, and then it's x times that exponential minus m omega x squared over 2h bar. Okay, so when you plug this one into this equation, what you end up finding, again, it's a little bit tedious. It's actually more tedious because the derivative, second derivative is going to be more complicated. This implies that the energy you get out, which is corresponding to the, when I have a, order 1 polynomial in front of the exponential, this gives 3/2, or 1.5 times h bar. Oops, I'm going to run out of space. I'm running into myself. H bar omega. And so on and so forth. So on you go. It just keeps on going like that. And so you might be asking yourself, well, how did you find out what these polynomials were? And the answer is complicated mathematics. But it's not terrible, but it's relatively complicated how to get it. But it was solved by mathematicians back in the mid-1800s. So when quantum mechanics folks like Schrodinger that came up with the equation in the first place, when Schrodinger came up with it, he said, well, this is the Hermite equation. I'm a mathematics expert. If I wanted to solve this, I should go look in the books, the math books, and the math books had answers, it turns out. And he found out that there were these energies. So what this means is if you can start to notice what the pattern here is. If you do it for n equals 2 for the second order polynomial here, which is more complicated yet, you would end up getting that E2 is equal to 5/2 h bar omega. So that tells us that the energy associated with the nth order polynomial multiplying the Gaussian here, the energy associated with that is n plus 1/2. So an integer plus 1/2 times h bar omega. And there we go. Those are the energies that are associated with the harmonic oscillator solution. And that's it. Okay. So those are our energies, and then the wave functions would look something like this. It's a polynomial, which we could sort of write it down here. I guess I'll write it. Psi n is equal to some constant, which I'll call a sub n. There's a different constant in front of, and these are the normalization constants. This is when you integrate this over all space, that constant, the total integral over psi squared should be 1. So that a sub n then is built to do that. So then I've got, and what you have is the Hermite polynomial of order n, which is a function of x, times the exponential e to the minus m omega x squared over 2h bar. And these are the general solutions of this equation. You just have to look up what the nth order Hermite polynomial is with the particular coefficient sitting in front of it and all that sort of stuff. So those are the solutions to the harmonic oscillator problem. So the other interesting thing about the harmonic oscillator problem is how generally useful it is to solve. Having a solution for this in your back pocket is really valuable because, and I'll sort of try to show you why. I explained it a little bit in the lecture notes, but I'm not sure it's super clear, so let's make it as clear as I can here. So I'm going to only erase that part because I don't want to erase that solution right there, but we'll get rid of that, and then we'll get rid of this. Okay. All right. So the idea is this. If I have, let's say that I have any old potential that an electron can experience, and maybe I'll just draw sort of a random one. So let's say that the potential energy that an electron experiences as it moves in some position, let's say it's just a really weird one. Okay, so I got sort of this weird, potential that is, it dips down, then it goes up, and then it goes down again, goes back up, and whatever that is. This spot right here, so I'll mark it with a red dot. So there's a minimum. Okay, so that minimum there, that little red dot, if you look at that spot in the region around that potential, what you'll see is that near the bottom, near where that minimum is, where I've made this dashed line, this sort of curved dashed line, you could fit that. You could say, well, that near the bottom of that minimum there, the potential actually looks like a harmonic oscillator potential around that spot, because what's the harmonic oscillator potential look like? So if I were to draw the harmonic oscillator potential, that's 1/2 m omega squared x squared. That looks like a parabola. And you'll notice that so this is the actual harmonic oscillator potential, that dashed line there kind of looks like the harmonic oscillator potential. And I could do the same thing here as well. Near the bottom of that particular potential energy minimum, like right there, that function right there sort of kind of approximates around the bottom, at least it's approximated by the harmonic oscillator potential, which is valuable then, because what that means is that, at least as an approximation tool, the harmonic oscillator potential is awesome, because anywhere where I have a bound state where an electron is in a particular minimum of its potential energy, where it could be bound or something like that, it's going to act like it's a harmonic oscillator. Okay, well, that means that the harmonic oscillator is the solution to tons of bound state problems, at least one-dimensional bound state problems. And at least it's a good approximation to it. So for the most part, electrons that are in bound states in some arbitrary potential are going to act sort of like a harmonic oscillator, which that's good. Means now we've solved the bound state problem, at least the approximate bound state problem, for pretty much any bound state, which is interesting and useful. The other thing to consider here then also is the following. So if an electron is in a bound state, what the harmonic oscillator problem says is that, well, there's a ground state of that bound state, and then there's excited states of the bound state. The ground state is when n is equal to 0, and the first excited state is when n is equal to 1, and the second excited state is n equal to 2. So it's possible that in this, there is an energy associated with the ground state, and notice it's not 0. And then there's an energy associated with the first excited state, that's n equals 1, and then there's an energy associated with the n equals 2, and so on and so forth, and they're all equally spaced. This is half, n equals 0 gives half h bar omega, and then this one gives 3 halves, and then that's 5 halves, and then it'd be 7 halves and 9 halves, and so on and so forth. And the same thing would be true in these bound states here, okay, that are inside here. At least the approximate. As soon as you get to higher excited states, then you start to notice that it's not exactly a parabola there. But let's consider the case for electrons sitting in a potential somewhat like the harmonic oscillator. Let's say it's exactly like the harmonic oscillator, but it doesn't have to, it's, for our purposes, we can approximate that for now. Okay. Then if we do that, and we think about that, now here's the thing, and this is a little bit into electricity and magnetism theory, that if you study radiation, like if I have an electron that's accelerating or something like that, like it would be under the harmonic oscillator potential, if it's accelerating, it's going to radiate. So when it radiates, it turns out that the amount of radiation that is going to be given off, classically speaking, is going to be related to the dipole moment that the electron experiences. To calculate the dipole moment, you multiply the charge times the separation of the charge. So the dipole moment of an electron that's in this bound state right here would be calculated like this. It would be psi of m times x times, so this is x, this is actually the variable x, times psi of n of x, and then you would integrate that. This would tell you the dipole moment of the electron as it moves from between states N and M. Okay? So that would be the dipole moment. And the radiation is going to be proportional to that, the degree of radiation. And that's the thing. If you're talking about radiating, you're talking about giving up energy. So we're talking about this little calculation here, which allows us to calculate the electric dipole moment that is involved in transitioning from state N to state M. Well, that's going to have to do with the radiation of a photon. So this is telling you something about the probability of the electron transitioning from state N to state M. And when it does so, it's giving up a photon in the process. So the question then is, what are the possible values of N and M that such a transition could occur for? Well, it turns out that this integral is 0 under all circumstances unless a specific condition on N and M exists, namely that N is equal to M plus or minus 1. So N and M can only differ by 1. Okay, so N is equal to M plus or minus 1. Okay, so if we're talking about an electron then radiating a photon, giving up energy in the form of a photon, in transitioning going from state N to state M, the only way that can happen is if N is bigger than M by 1. It changes, like this goes from 3 to 2, or from 5 to 4, or from 2 to 1, or from 1 to 0. That's the only way that this integral is non-zero. Which means, if the integral is non-zero, that means that there's no probability of the electron performing that transition and giving up radiation in the process. Okay, so the issue then is, what we then see is that this shows that the energy in transitioning from N to M, from state N to state M, the energy that must be given to the photon in that process is equal to h bar omega. Because all states of the harmonic oscillator differ in energy by 1 unit of h bar omega. Okay, now remember omega is equal to 2 pi f. If we want to go back to the frequency, the omega frequency is radians per second. The f frequency is in hertz. H bar, remember, is h over 2 pi. This is the Planck hypothesis, right? Remember back when we first started talking about quantum mechanics, we said that Planck said, well, the energy of the quantum modes inside of the black body cavity is proportional to the frequency, and that sort of stuff. So he said, well, the photons have particular energies which are proportional to their frequency. The solution of the harmonic oscillator potential tells us why Planck's guess was actually, after the fact, it's good physics. But it took, notice how it took, working out a lot of quantum mechanics before we actually got to the idea that his first hypothesis was right, other than the fact that it explained the black body. It turns out that from first principles, it turns out to be correct. That electrons in bound states inside of the black body that are radiating because of their wiggling in the harmonic oscillator, as they transition, they always give up an energy equal to h bar omega, because when they transition from one state to the next, they all, dropping down in energy, they always lose h bar omega. They can't lose more than that because the wave function wouldn't, the wave function integral would give a probability of 0 for that transition occurring. So they always give up h times f. So that was good news, but it also shows you the wide realm of applicability of using the harmonic oscillator potential as a basis for understanding physics that doesn't look necessarily at first blush like a harmonic oscillator. Okay, so there's sort of the solution of the harmonic oscillator. I don't know if there are questions on homework or anything like that, but we'll see. So if you do have questions on that, go ahead and let me know in the chat. I'm not sure I have anybody watching, but I'll make assumptions that there are at least. So let's talk about sort of the second lecture then. So this is that was sort of what the first lecture was about. I'm going to clear out this because we don't need that for what we're going to talk about subsequently here. The situation that we're dealing with now is a different type of potential. And this one is a step potential, kind of like what we did with the particle in the box. So the solutions, we're going to have a lot of similarities with the particle in the box. But I'll put the look of the potential here now. I drew it in the lecture notes, but it looks something like this. So let's say that we have a situation where here's the y-axis, and then here's the x-axis, and then here there's x equals 0, and the potential is 0 for all values of x less than 0, and it jumps up at x equals 0 to a value of v0, and it goes forever out to v0. So the potential just increases. So what we have here is sort of a barrier. It's not an infinite barrier like the particle in the box, but we have a barrier that extends out to x is equal to infinity. Okay, so that's the solution, or that's the situation that we're going to consider. And we're going to be looking at scattering. So what this means is I've got basically two regions of space. I've got region number 1, and I got region number 2. Okay, I just put the, let me make it symmetric here. There's no reason why I put the region in the upper value there. So I'll just put it down here, so I'm labeling them both the same way. So I've got region 1 and region 2. Region 1 is x less than 0. Region 2 is x is greater than 0. And then x is equal to 0 is where the potential exactly changes from 0 to v0. Okay. So I think you can see that in region 1, the value of the potential is 0. So in that region, Schrodinger's equation becomes, and I'm going to use the wave function, I'm going to label it 1 to indicate that we're talking about the solution in region 1. Psi double prime, so this is the second derivative of psi with respect to x. Okay, that's going to be equal to negative 2m, this is the mass of whatever quantum is moving, e over h bar squared times psi, times the same psi. And it's the psi in region 1. Okay, so this is the free particle. We're going to say that the particle has some particular energy E. We don't know what that value of energy is. Let's just say it's an input. Like I know that this particle that is, this quantum that exists in region 1 has energy E. It is whatever it is. Okay, it's unbound, so it could have any energy really. The boundary conditions don't limit what it would be. All right, so the issue though is that we should consider what's going on in this region right here. What we're going to be talking about and considering is the case where I have particles that are incoming, moving from the left towards the right, and hitting the barrier. The possibility exists though that some of those quanta could scatter back. So I should have both left moving and right moving particles existing in this region. So we could use sines or cosines in this. It turns out that using sines and cosines in this region, because this is sort of the second derivative is equal to minus some constant times the original function back, it looks like they should be sines or cosines. It's a little bit inconvenient to use sines or cosines, though, to solve this one, it turns out. It's easier to express it in terms of plane waves in x. So I'm going to say psi 1, the expression in psi 1, the wave function in region number 1 is going to be some constant a times right moving plane waves, which plane waves are expressed as complex exponentials. I guess I'll call that K1. Okay, so this is actually a plane wave solution. It's a complex exponential. It's very similar to the to sines and cosines, not exactly, but this is a solution. And then that's one that's moving to the right because this is positive. And then and it's got its own coefficient, and then there's a left moving one. And it's going to be, again, a complex exponential. And it's left moving because of the minus sign there. The sign in front of it tells you which way the plane wave is propagating. Okay, now what's K1? K1 in this case, well, I'll put just K1 squared is equal to whatever the coefficient was inside of psi 1 without the minus sign. So K1 is 2m times the energy of the particle, or the quantum, over h bar squared. Okay. So what we're saying then is I've got a set of quanta. They're traveling in from the left-hand side, moving to the right, moving towards the barrier. Some of them bounce off of the barrier and bounce back towards the left. A then is the coefficient which tells you about how much, well, it's the coefficient for the right moving particles. This is, we can't really normalize this because it's basically, it's kind of like it's a rate. It's a number of particles. It has to do with the probability that particles are coming in from the right. So what we're going to see, though, is that, let's look at region 2 and see how this is a little different. So psi 2, double prime. So this is the Schrodinger equation. The second derivative of the wave function in region 2. So second derivative, that's equal to minus 2m times e minus v0 now. Just a constant over h bar squared times the original wave function back psi 2. Okay, so that's that. Now we have a couple of things to consider with this one. The things to consider are, well, the energy that, this thing in parentheses here, this quantity in parentheses, could be positive or negative. Depends on the energy of the incoming particle, the part that the particles have when they're in region 1. If the particle has more energy than in region 1, it has more energy than the potential, so E is greater than V0, then this is a positive number, which means this overall coefficient would be negative because that minus sign there, and it basically going to have the same sort of form as this one, where I've got that the second derivative is equal to negative some positive constant times the original function back, and the solution will be plane waves. That's if E is greater than V0. Okay, so the solution would be plane waves. The interesting thing, though, here is if there's not a chance for plane waves to be moving from right to left. There's no left moving plane waves here. The reason is if what's happening is if particles our situation is the scattering problem, where I've got a stream of incoming particles hitting the barrier, some of them bouncing off and some of them going in, well, then there's no chance that particles are moving leftward in this. They're either moving to the right or they don't exist. So this solution here is going to be the solution to this, and I've run out of space. But the solution is going to be something like, if E is greater than V0, it's going to be something like C, a constant, times e to the I, right moving particles now, times K2 times X, where K2 is going to be the same sort of thing. K2 squared is going to be 2m e minus V0 over h bar squared, rather than E, because this is the constant. But that is true only if E is greater than V0. If E is less than V0, then this thing here, this quantity in parentheses will be negative, which means that this overall thing would be positive. So now that's a fundamentally different sort of differential equation. The second derivative is equal to a positive constant times psi. And now the solution of that is actually an exponential. Okay? So that's a little bit different situation. That exponential, and I talk about this a little bit in the lecture notes, and that's because if you take the derivative of an exponential, you get, you derivative of a regular exponential e to the alpha times x, I called it in the lecture notes. You take the first derivative of that, you get alpha times e to the alpha x. You take the second derivative, you get alpha squared times e to the alpha x. You get the original function back, but with two factors of alpha, whatever the coefficient was in front of x in the exponential. So there, you do that. So, and that works for either e to the minus or e to the plus alpha x. Either one works. Now, so that would mean that if e is less than v0, I would have a situation where there would be the possibility of two exponentials, c times e to the negative alpha x plus d times e to the positive alpha x in this expression here, or in this region here. There's a problem with one of those, though, that I mentioned. And the problem is that the e to the positive alpha x, alpha is a positive constant, which it would be. This would mean, if I have positive alpha x, notice what that would do. That would mean that the wave function in region 2, that exponential that's positive, would grow without bound here, which is not normalizable. It doesn't really make sense. It means that the particle would have an infinite probability of being infinitely far away, which is kind of dumb. It doesn't make a lot of sense. So that means that the particle, if it was scattered, if it was transmitted into region 2, it would have an infinite probability of being infinitely far away, which doesn't make any physical sense. So what we do is we say the following: d has to be 0. The only thing that we get, the reasonable one, is that we have a decaying exponential inside of here, and then we would have, again, c. But the c would be, the coefficient for that particular situation would be c times e to the negative alpha x, would be, the decaying exponential in here. So that's the solution for e less than v0. The solution for e greater than v0 says that we have a shift in the constants here, shift in the wave number k2 from this value tm e over h bar squared to t2m e minus v0 over h bar squared as I cross the boundary. So what it means is the wave number, the wavelength of the plane wave solution shifts when I go into region 2 from region 1. So then what you do is you say, well, what are the scattering problem then is to solve for the probability or the rate at which particles get reflected as opposed to transmitted. And that is going to have to do with, let me give myself a little bit of space here. Okay, so that means that what we're looking for, the reflection coefficient would be equal to the absolute value squared of b over a. Okay, which has to do with the probability that the quanta gets reflected compared to what the original intensity was. And the transmission coefficient, and this is for, particles are coming in from the left, they hit the barrier, some of them come back, so that's the reflection, and then some of them are transmitted. And that has to do with the probability that the particle actually ends up in region 2. That's going to be the absolute value of c over a squared. And the thing is, the transmission coefficient, since particles are traveling, the particle will be traveling at a different velocity in this region here, because it has a different wavelength, has a different wave number. Actually, if you want to talk about the rate of transmission, the transmission coefficient is the probability of transmission times the velocity, or the relative velocity. So we'll do k2 over k1 to represent that. K2 is related to the velocity. of the particles. And so this is basically the relative velocity of particles traveling in here compared to the velocity over here. So this one, if K2 is smaller than K1, it's traveling at a slower velocity, so the rate at which particles move away from this boundary is going to be the probability that actually is in region 2 compared to region 1. That's the C over A squared. And then you got to multiply also times the rate at which the particles are moving, having that probability. So that's why we have the ratio K2 over K1 there. Okay, so how do we find what B over A is and C over A is? Well, you actually have to apply the boundary conditions. The boundary conditions are that the wave function in region 1 evaluated at position 0 has to be equal to, this is the continuity condition, the wave function at region 2 evaluated at 0. Okay, remember what the wave function at 1 was. I know I erased it, but if we're following along, it's A, and it was e to the I k1 times x, but at 0, that would be 0. E to the I k0 is e to the 0 power, which is 1. Okay, and then we also had b, this is in region 1, remember, times e to the, negative I k1. But that really doesn't matter because, again, we're going to multiply times 0, and it's e to the 0 again as well. And then you get the same sort of expression here in region 2. Remember that one was, it was c times e to the only right moving particles now? Yeah, it was k2, but again, it was 0. So what this tells us is that A plus B equals C. Or alternatively, you could say this also implies divide the whole equation by A, 1 plus B over A equals C over A. Okay, so that's the first condition. All right, now that's one of them. There's another condition, though, that needs to be, so this hasn't finished our problem yet. We're still looking for B over A and C over A. We have two equations and two unknowns yet. The thing is, we still have the solution, or the condition, that in addition to the wave function being continuous across the boundary, the wave function also has to, its derivative needs to be continuous over the boundary. So that's psi 1 prime at 0 should be equal to whatever psi 2 prime is evaluated at 0. Okay, so all you have to do is you've got to take the derivative of psi 1 prime. Okay, so now what do we get? We get, so I'm kind of use this, imagine that there's an x here. If I was going to take the derivative of this, what do I get? I get I times k1 times e to the I. So I get, when I take the derivative of this, I get an extra factor of I k1 times the original wave function back, which when you evaluate that at 0, again, you get 1 for that, so you get this expression. Okay, so there's the first part. This one, it's negative I kx in the exponent, so I would get minus I times k1, and then times b, because then when you evaluate that part of the derivative at x equals 0, at x equals 0, you get your 1, and then this one, if I do I get I k2 from differentiation of the exponent of the exponential, and then c times e to the I, again evaluated the derivative at x equals 0 for the derivative, and when x equals 0, you get 1 there. All right, so this is the other expression. Notice I can get rid of the i's here, but the whole point is what I get is I get k1. All right, that's I could rewrite it a little different. I get also then the expression something like 1 minus b over a is equal to k2 over k1 times c over a. So all I did there is first divide both sides by k1, that's k2 over k1, and then divide both sides by A. And then that gives me the 1 here, B over A there, B over A. So now I've got an algebraic equation in B over A and C over A. I can solve for them individually, and you get what we get in the solution. So I wanted to sort of show how that kind of works a little bit. So hopefully that's moderately clear about how that works. So then if I solve for B over A, it gives me some formula. I don't remember what it is off the top of my head. I could look at my lecture notes, but it tells you what B over A is, and then when you square it, you get the expression for the reflection coefficient. And then when you take C over A squared and you multiply times K2 over K1, you get the transmission coefficient, which is the rate at which particles are transmitted into region 2 from region 1. Okay, and so then that tells you what the solution looks like. And it also works for the exponential if you like. Okay, so a couple of things about this one-dimensional barrier then, just to give you a sense about how this works. If E is greater than V0, I have some percentage of the particles will travel into the barrier, pass through, some will be reflected. That's different than a typical problem where, like, I throw a ball at a wall. If it like gets over the energy, it'll just go, it'll escape. It'll, like if I miss the wall, it'll leave. It'll just keep going. But if it hits the wall and bounces off, then it'll come back. So classically speaking, you wouldn't get this some are transmitted, some are reflected situation. So that's a little bit weird, but this does act like light does. Remember what happens with light is that when you reach a barrier, some of the light is transmitted into the glass if it's transparent, some of it is reflected, that sort of situation. So this is kind of putting particles or quanta like photons, which correspond to light, or electrons that would do the same sort of thing. The electrons kind of act like light do at this potential barrier. The other thing that's a little bit different than the classical situation is if you throw a ball against a wall and it doesn't have the energy to pierce the wall, it bounces back. Definitely 100% bounces back. Doesn't go like, it doesn't like, some of the time it might make it through the wall or something like that. Either it does or it doesn't. In quantum mechanics, if the energy of the incoming particle is less than the potential energy associated with the barrier, what happens is the particle will have some exponential decay of the wave function, so there will be some probability that the particle can be found inside of the barrier, which is weird. It's unusual, but it is the way that it actually works. And you might be saying to yourself, but wouldn't the particle have negative kinetic energy in here? And they go through a lot of detail about how that works in the book. But I'm going to give my short, sweet version of what they're trying to explain there with a ton of mathematics. Short, sweet version is the following. Actually, the way that you calculate the kinetic energy of a particle is you say it's p squared over 2m. Here's the deal. If we're saying the energy of a particle that's incoming from the left here, traveling towards the right, it's actually uncertain. There is some uncertainty in the energy of the particle, which means there's some uncertainty in the momentum of the particle as well, because E is equal to p squared over 2m. So what I'm saying is the fact that you aren't sure where the particle is and how much energy it has means that there's some probability that its uncertainty in its position might carry it inside of the barrier. And its energy might actually have been a little bigger than you thought because of the uncertainty in the energy that it has. So that means that rules that appear to be hard and fast in the classical world are not quite so hard and fast in the quantum world. It means that we don't necessarily know the particle's energy is less than V0. There's an uncertainty in the particle's energy. There's a distribution of energy. This is the quanta. You never know the energy perfectly. And that might mean then that the energy actually allows it to penetrate some distance in here. The way that they also calculated it is, it said, well, if we are finding that quantum is actually inside of the barrier here somewhere, that the distance that it could be away from the edge at x equals 0 is relatively small, has to do with alpha. That's the rate at which this thing decays. If that's true, it turns out that if the quantum is actually in this region, there's an uncertainty in it, which means there's an uncertainty in its momentum, which means there's an uncertainty in its kinetic energy, p squared over 2m, and that's actually enough to give a positive kinetic energy, or at least allow it to have a zero kinetic energy. So that's what they're saying in the book, is that the uncertainty principle sort of comes to your rescue here to give you really non-weird results. It's weird, but not in a completely devastatingly weird way, like having the idea of negative kinetic energy would be devastatingly weird. It would mean you have particles have an imaginary velocity, which that is, quantum mechanics is weird, but it isn't that weird. It's not imaginary. Okay. So the next sort of step to consider is the case where we're dealing with a finite barrier. Okay, and that was the subject of the last one, and this one is the algebra on the solution for the square barrier to apply the boundary conditions is extremely tedious. It's like 4 or 5 unknowns, 4 equations, and 4 unknowns or something like that. So the mathematics of it is relatively tedious. But let's outline it, and then I'll just go from there. So the idea then is, what we have is a situation where we're going to have to divide this into 3 regions. We've got particles that are going to be incident on the left, from the left, moving to the right, which strike a potential that has a finite size and height. The height is v0. It starts at x equals 0, but it stops at x is equal to a. And then the potential is 0 for all values of x that are less than 0. So I've got this little hump in potential. And the solutions are probably what you sort of imagine. So we're going to have 3 regions, sort of region 1, region 2, which is inside the barrier, and region 3, which is outside the barrier but to the right of A. So those are our 3 regions to consider. Region 1 and region 3 have very similar solutions, except, again, region 1 can have both left moving particles. Again, we're assuming that this is a scattering problem, so the quanta, the stream particles that are coming from the left, moving to the right. They hit the barrier at x equals 0, and then some of them could scatter back. Some of them could go into region 2. In region 2, we have a couple of things to consider, but the one that is probably the most interesting is for the case when E is less than V0. This is the case where, classically speaking, the particles would simply bounce off of the front barrier and never get into the barrier itself. In quantum mechanics, it doesn't do that. There's an exponential solution inside of here that there's an overall exponential solution inside of here, and then so that particles can exist in here, and then there's another free particle solution out here in region 3, but we only have right moving particles in region 3 because that. So those are the situations that we would have to consider. So what we have to do is, the solutions that we have is that in region 1, psi 1, we have A times e to the I kx plus, these are particles that might have been reflected from the front barrier, or from the back of the barrier for that matter. It's just left moving particles scattered from the barrier in general. Negative ik x, where k is the square root of 2me over h bar squared. In region 2, we have c times e to the minus alpha times x plus d times e to the positive alpha times x. And notice that we can keep the positive exponential here because this region is bounded by a, so it would never, the probability density would never get infinitely far away. It never has a chance to grow arbitrarily large because x is limited to being between 0 and a in region 2. So we got to keep d. We can't throw it away. So it's a mixture of those two. And alpha now is 2m v0 minus e over h bar squared. That's guaranteed to be a positive number because e is less than v0. And then psi 3, oops, that should be a 3. I'm going to make it a 3. Okay, psi 3 is, I'm going to use, so that I don't have to use e for the exponential, we're going to use f like they did in the book. And we have right moving particles. And it's the same k as in region 1 because in both cases the constant in front of the wave function in this, on the right hand side of the Schrodinger equation would be the square root of 2me over h bar squared, quantity squared. So you have something like this. All right, so here's the deal. The solution of this is, as I mentioned in the lecture notes, the solution of this is, the way you're going to find this is you're going to find everything in terms of a. So you could divide everything by a here. All right. But the thing to consider is we have two boundary conditions to work on. We've got the derivative, or that, first of all, psi 1 and psi 2 should be the same at x equals 0. So if I put x, so that would say a plus, so if I put in x equals 0 here for each of these, I would say, okay, it would say a plus b is equal to c plus d. All right, there we go. There's one equation for my 5 unknowns here, a, b, c, d, and e. Then what we have next is the idea that the derivative of should be equal on each side of the bound, at x equals 0. So I do the same thing as I did before for this one. I've got, when I take the derivative of this, I get ikx, and then for this one I get positive ik, negative ik there. So this gives me, when I evaluate it at 0, it's a times k minus b times k is equal to, and then do the same thing here. You got a negative alpha and a positive alpha. So negative c times alpha plus d times alpha when I evaluate it at x equals 0. So k times a minus b is equal to alpha times d minus c. Okay, so there's another, that's another. So there we go. That's two equations. Now, we got to do, we also have to have what happens, the boundary conditions applied at a, because region 2 and region 3 wave functions need to be the same at x equals a. So again, I do the same thing here. So that would be c times negative alpha a plus d times positive alpha times a is equal to f times ika. And do the same thing for the derivative. So I'm going to have 4 equations. My 5 unknowns are a, b, c, d, and f. Divide everything by a, because what we really want are b over a and f over a. Because b over a is the reflection from the barrier. F over a is the transmission coefficient. So do that algebra. 4 equations and 4 unknowns. Super fun. Do the 4 equations and 4 unknowns. Solve for it. You can get f over a and you can get b over a. F over a is the transmission coefficient. B over a is the reflection coefficient. The transmission coefficient then is, after that tedious algebra is gone through, and I didn't want to show it to you, it is a serious pain. But once you got it, it's Yeah, got the transmission coefficient. It ends up being this complicated function involving the hyperbolic sine. The hyperbolic sine, or the sinh for short, just to remind you what that is. The sinh of the quantity x is equal to, this is the definition, it is e to the x minus e to the minus x over 2. That is the hyperbolic sine. So if your calculator doesn't have a hyperbolic sine, you want to evaluate that transmission coefficient, you can plug this in, which is what I had to do because my calculator doesn't have a hyperbolic sine function on it. Well, it probably does, I just couldn't find it. So this is interesting. This describes then this transmission coefficient then is describing something that cannot happen in the classical world. It's like having a barrier and the energy is of the particle that's going to run into the barrier doesn't have enough energy so that it can have kinetic energy to carry it through. I mean, if you have more energy than the barrier, like your energy is bigger than V0, then all that happens is when the particle gets to the barrier, it slows down, and then when it leaves the barrier, it speeds back up. This is kind of a non-physical situation, but it's a situation. It is what it is. All right, it's just but that would be what would happen there is if it receives this potential energy expression and it moves, it would slow down, then it would speed up as it leaves. That's what happens. That would be the dynamics of it. In classical physics, though, if your energy isn't big enough to go, to allow you to have kinetic energy in this region here, it would just reflect off and bounce back. And the reflection coefficient would be 100%, and transmission would be 0. It would never go, particle classically never go through. In quantum mechanics, because of that possibility of the particle actually existing inside of the barrier, there's the possibility that the particle gets through. And you might be saying to yourself, yeah, but it would slow down, it would do all this sort of stuff. The thing is, it doesn't do that. And what I said in the lecture notes, I wanted to clarify that. What I say in the lecture notes is you shouldn't think of this thing as like burrowing through the barrier, like it drilled through it somehow. That's kind of what tunneling sounds like. It's like it dug through somehow. It doesn't dig through. The barrier doesn't slow the particle down. The rate at which the particle is moving on the right-hand side is the same as the rate on the left-hand side. Notice that the Ks are the same. Wavelengths are the same. Frequencies are the same. Energies are the same. On both sides of the barrier. It doesn't lose energy going through the barrier. It doesn't. But there's a probability that the particle could end up on the other side traveling to the right. That it could be transmitted through the barrier, even though classically speaking, it couldn't have gone through. Quantum mechanically speaking, it can. So that's hard to maybe interpret, but it goes back to the idea I was talking about with the step potential that we talked about in the previous lecture notes that I talked about a little bit ago. There's an uncertainty in the position of the particle. As it comes through here, as it's moving here, as the center of probability of the particle gets closer and closer to the barrier, there's a non-zero probability that the particle's position is actually over here on the other side of the barrier. That means that the particle isn't where you think it is. Of course it could travel through that, quantum mechanically speaking, because you didn't know exactly where the particle was in the first place. There's some probability that it could be over here. And that is, in fact, why there is a transmission coefficient here. Because the uncertainty principle allows the position of the particle to be uncertain. It doesn't, and in that case, it's not that the particle is burrowing through the barrier through some physical mechanism that's allowing it to like dig through it or something like that. It ends up over here. That's where the particle was. That's where the particle is. And it'll continue propagating to the right like the rest of the particle did. So that's the sort of situation that in quantum mechanics it's hard to think of it classically and have it make sense, but quantum mechanics allows for different effects to happen. And if we lived in the quantum realm, if we lived like at very, very small scales, this wouldn't seem weird. It would just be the way it is. It wouldn't be counterintuitive. It would be intuitive. And Yeah. So that's sort of it. Now, this effect, this quantum mechanical tunneling effect, is actually got an application to it. The scanning tunneling microscope makes use of that, and I gave a little picture that describes in the book sort of what goes on with quantum mechanical tunneling, scanning tunneling microscope. If you put a really, really sharp point on like a needle or something like that, and you bring it close to an object, and you put a little bit of a voltage between them so that there's the possibility the electrons could jump across the gap. Classically speaking, they can't leave the gap because they don't have enough energy to do so. You haven't put the voltage to be large enough so that the electrons could, like, the voltage would cause them just to leave the surface and overcome the work function of the metal and just, pop right across. So it's kind of like having a barrier like this. There's a barrier of the gap in energy that is necessary for the electrons to leap across. The thing is, the closer you get to the surface, the smaller the gap gets. And because the transmission of electrons across the gap between the needle of the scanning tunneling microscope and the surface of the sample that you're trying to map out, since that distance is so sensitive, or the transmission coefficient is so sensitive to the separation spacing and the gap height and all that sort of stuff, if you move just an atom's diameter closer, you can change the current of transmission. You can change the transmission coefficient by a factor of 10,000, which is easily measurable. So this is an extremely sensitive way to measure very, very tiny distances. So the scanning tunneling microscope can, because of that effect, it's easy, relatively easy, to use the effect of tunneling to map out a surface with a sensitivity, with a precision that allows you to measure and map individual atom thicknesses of that surface. So, really, really good for mapping surfaces. So, I'm going to end it here. I don't see any folks watching today, which is unfortunate. Hopefully this was useful to you. I know I just went over notes and stuff like that, but since I didn't have any questions to answer for you, I hope it was valuable for you to see some of this. If it wasn't possible for you to be on the stream today for some reason that's common to all of you or something like that, please let me know so that I can schedule the streams better for you. And please use the discussion boards to do that. So I'm going to end it here. Hopefully you found this useful. If not, please let me know what I can do to make this better. We'll see you next week and have a great rest of your week. Goodbye for now.